the elemental case. So where his was better, it's very, the ones I've looked at so far, it's not as good, but a few cases where his was actually better with sodium iodide, and there's ample things that could have went wrong. We had very much difficult time with the barium case, but these are things that we need to look at and figure out why exactly this happened. There's a few weird cases where they both neither actually give a good approximation. They both at one point in time under and overestimated. So these states are incredible to look at because neither one is giving a right on approach. And then this is what we want. This is like an perfect agreement. So if we can figure out what gives us this using any method, then this would be a very good stepping stone into the technology. So what did we come to see from this is basically more valence states yield better results because you can vary more things, because the valence state is what most of the important interactions are happening in between. But it does come at a high computational cost. Generally, there's good agreement between these, and why I say that, it might be that he shows more core states because if you can get the similar results for the approximation with less time, then it might be better. Or this is just an approximation, so maybe it doesn't need that much precision. And the diagram picture I'm going to leave out, but it's basically that there's a group or a region of acceptable values, and perhaps that if you're in this range of values, and you'll get convergence, but between some part of this region might yield better values, but that's something that time and more testing will define. And finally, I'd like to acknowledge the NSF grant that funded our research, the Wake Forest Cluster Computer, Dr. Natalie Hallsworth, Cameron Cates, and Zachary Pitcorn, and also Chow Chow. Francois Gillet and Mark Charant as our French collaborators. And also I'd like to give Cameron some congratulations. He created some very good codes over the summer to expedite our research, and that was extremely helpful. So with that, thank you very much, and if you have any questions.
About 2 minutes or so for questions. So, you have any questions for Jim?
What's the figure of merit that you're using to determine whether your results are worse or better?
The V2K.
It's got your visual abilities, but
yeah.
I couldn't tell if there's some.
The black dots is actually what was the comparison. That's what we were considered as the standard LFPW plots. It's used in a completely different approach. It doesn't use zero potentials at all, and it's a little bit of an older code and more accepted. And there's over, I think, it's like 2,500 institutions or research groups that use it. So that was a good thing for us to look at and use that as a standard, especially because it was a completely separate approach that didn't involve the zero potential creation.
Is there a reason why the barium sulfide was different than the others?
Yeah, it was shifted, and barium was one of the very last things that we worked on at the end of the summer. It might just be because it's more of an unstable test, or our database had a very large outlier critical amount. And barium was the only case, and I think all 3 of us worked on it, and that was pretty much the best thing that we could get. I think that was the only one we could actually get to converge at all.
So you would expect the same thing with any compound with barium?
Possibly. Basically, it's just the sulfides that we've actually tried to look at specifically. But again, that was one of the later things we did in the summer, and we were trying to look at more of the initial elements in the periodic table. But besides that, I really am not sure why that was such an outlier group. And it's weird because I was trying to find huge differences between our data sets, and it was either his was very close or exact, or it was like that and completely off center. And as while that is the case, I'm actually trying to look at specific values because the data set that we created for each element it can't be changed throughout. So it has to be the same from the very beginning, because if you change it at all, then it's going to affect all the results from that point on. And it's very hard to look at what one single factor causes all this change, because as you said, that wasn't even a full input file, that's just the perfect data. And change one thing on there, then it's there's 28 possible things you can look at for each one. It's hard to run the entire process
Chairman Gates is also doing work